So we want to talk about design of compensators in frequency domain. And we have seen how you might design the compensators lead lag or lead lag in the S domain using the Routh-Lucas method. And if you remember, when we did the Routh-Lucas method, it was based on transient response, right? So if you remember, we mentioned stuff like rise time, settling time, or maximum overshoot. So the Routh-Lucas again was based on transient response. On the other hand, the frequency response is based mostly on steady state behavior, although it might indirectly or implicitly have some info about the transient response. For example, we learned that if somebody is giving you info about resonant frequency or resonance peak value, that is indirectly referring you back to the damping ratio, right? So this is what we had, let's see, over here in this slide, right? So if I give you MR, then you can find zeta, and if I give you omega R, then you can find omega N as well. So we kind of indirectly can find transient response characteristics, zeta and omega N, and then based on zeta, omega, and everything else in terms of the parameters and measures we learned in this chapter. And the other one, if you remember, was for a standard second order system. If I give you phase margin gamma, then you can, from this equation, nonlinear equation, or in a region of zeta between 0 to 0.6 or gamma between 0 to 60 degrees, you can just divide gamma by 100 and get zeta approximately. So you can, yes, get zeta based on phase margin for a standard second order system too. So, and one other good thing that frequency response approach has that I mentioned several times is not always you have the physical model of the system, the mathematical model of the physical system. You do not always have it. Sometimes it is really difficult or impossible to model the system. So when you don't have the governing differential equation, you cannot get a transfer function, and you cannot do the Routh-Lucas. But I told you that you can consider the system to be a black box, send in harmonics with known amplitude and phase, and then get the output of the system and measure the amplitude and the phase of the output and compare it against the input. And then you can get the magnitude and phase plots like the Bode plot without even knowing what's going on in the system. So you can get these frequency plots without even knowing the actual mathematical model of the system, and that's a big advantage. Now, one other thing that we need to mention is in the frequency domain, the low frequency region, the region close to the origin, indicates steady state behavior of the system. The mid-range determines relative stability using margins, and the high range determines the complexity of the system. And you might say, okay, where have you talked about this? So I refer you back to the slides. So let me show you where in our lecture we talked about these. So the first one, the complexity, was here. If you remember, I added something for you, and I wrote it, but then I added it to one of our future slides, and I mentioned that the phase of the system goes to what? N minus m times negative 90 degrees, and the slope at high frequencies goes to what? To n minus n times negative 20 decibels per decade, right? So if you remember, we mentioned it, and it is here too, right? Here. You can see it here, this part. So we are talking about high frequencies, right? Omega going to infinity. And then from that, we can infer what? N minus m. And n minus m is the difference between denominator and numerator of transfer function, which talks about complexity, right? Or the order. So the higher the order of the system is, the more poles and zeros it has, and the more complex it is. So when it says complexity, it's talking about basically n minus m, right? Which you can infer from high frequencies. Then it says low frequencies, we can infer something about the steady state. And yes, if you remember, that's this section here that we looked at where omega is going to 0. Then based on the type of the system, I can either find what? Kp, or I can find Kb if system is type 1, or if system is type 2, I can find what? Ka, and you know Ka, Kp, and Kv, they are directly related to what? A steady state error. So yes, in the left side of my frequency responses, when omega goes to 0, that's where I can talk about steady state error. And then what can you find in the mid-range? Well, the mid-range is where you have the gain crossover and the phase crossover frequencies, if you remember, right? Which we had them here, correct? The frequency at which the magnitude is 0, we call it gain crossover, and the frequency at which the phase is negative 180, we call it phase crossover. And then based on that, we can find phase and gain margin. And these are the mid-range frequencies. And in the mid-range, we know this phase and gain margin, they are indicators of what? Of a relative stability. So every portion of these frequencies would tell us something, right? From complexity to relative stability to steady state error. You probably see that nowhere is exactly telling me anything about transient response. And yes, that's correct. That's what the frequency response is. It's not directly talking about transient response. As I said, the only place that you might see something about transient response is the resonant frequency, right? And the resonant peak value, which are here, correct? So you can see MR is based on zeta and omega R is based on omega n and zeta, and also again this part that you can divide phase margin by 100 roughly, or solve the nonlinear equation and find zeta. So this is the only part that you talk about transient response. Good. So this is just a review of what we have learned so far in this chapter. Now, when we want to design a compensator, there are so many different plots, right? Bode, Nyquist, Nichols. Which one can be used? And if you remember again, last time I mentioned to you that we prefer Bode plots or Nichols over the excuse me, the Nyquist plot. And the reason is, when you do Nyquist plot, right, like, where's the Nyquist? So this is a Bode. Yeah, this is the Nyquist here. When you do Nyquist plot, the curve, the graph of the Nyquist, especially the magnitude of it, since it's indirectly shown in a Nyquist plot, you know, Nyquist plot is a polar plot. So instead of magnitude of the complex number and phase of the complex number, what you have is you have the real part and the imaginary part. So when you see a Nyquist plot like this, as I said, if this is for a gain in the compensator, gain of 1, now if you make gain to 5 or 6, you do not see a simple change in this graph. It's not like, well, this might be just shifted so many units up or down or left or right. Okay, so you cannot say, well, this is for k equal 4. That is not correct. It's not going to be simply shifted up or down. It has to be redrawn completely. But if you remember, in a Bode plot or Nyquist plot, we learned that when in the magnitude part of it, When you change a gain from one number to another, like this case, right? So this is for k equal 1, and then last time we showed that this is for another k, it was, I guess, 1.59 or something. All you need is, when you change the gain simply, is a vertical shift. And that vertical shift from k of 1 to arbitrary k is equal to what? 20 log k. That's the amount of vertical shift. So this is really good that you just shift the curve up and down. You don't redraw the whole thing and it takes a completely new shape. So that's why we always prefer the Bode plot, or if needed, sometimes maybe Nicole's plot. We do not basically try to go with the Nyquist plot. Okay, so polar plot like a Nyquist plot is not our preference. And when we design a compensator, first we try to just go with the gain adjustment, just like the root locus. We try to see if we just do a gain adjustment, is that going to give us everything that we need? Most of the time it doesn't. All a gain adjustment is doing for us, you're going to see, is modifying Kp, Kv, or Ka values and modifying the steady state error. That's all typically a gain adjustment would do for us, okay? Most of the times it's not giving us everything, because when we design a compensator, we typically are not looking for one requirement. Yes, we want to improve the steady state error, we want to reduce it, but there are also other types of things that we are after, like gain margin and phase margin, which gives us more stability. So not only, as I said, a good controller is what? The one that is fast, has minimal steady state error, and is stable, is the one that makes the system stable. And most of the time, not all of these come simply with the gain adjustment. You have to do a little bit of reshaping the Bode plot. So that's where not only we need a gain change, we also need to add a zero and a pole to the system. And that can be done either by a lead or a lag. They add 1 0 and 1 pole. One of them has pole closer to the origin and the 0 further away, and the other one is exactly opposite. And sometimes even lead or lag, I'll show you in this item here, that sometimes lead or lag alone cannot achieve all that we want, so we may need to combine them into a lead lag. Lead lag has 2 poles and 2 zeros, so it adds the order of system by 2 instead of 1. So lead or lag only, they add the system order 1 unit, but these lead lag, this lead lag compensator makes the system order up by 2. And we know that the higher the order of the system, the more complex it is, the more susceptible it is to instability, and it's not really a good thing to add to the order of the system, but sometimes maybe we have to compromise between 1 and 2 order change to get what we want. Now, why is it that a lead or a lag alone might not be sufficient? Well, because lead alone, what's the effect of lead? I'll show you in a second that lead pretty much acts like a high-pass filter, like a derivative. So it makes the system faster. It improves the transient response, okay? It can make the system faster, but it is not really affecting the steady state error of the system. It is not affecting the low frequency region. It is mostly affecting the mid frequency. And it acts again like a derivative, like a high-pass filter. So good thing is, yes, it improves steady state response. The bad thing is it is not affecting steady state error too much. Also, it might accentuate, it might magnify the noise effect of high frequencies. So if the input to your system is not just pure and clean and it has some noise, since this is like acting like a derivative or high-pass filter, it will make those noises even bigger and will ruin the system performance. Lag, on the other hand, acts like a low-pass filter or an integrator. So the good thing is, integrators would definitely improve the steady state response, but on the other hand, they gonna mess up the response time of your transient response. So they improve the steady state error, but makes the system slower. The good thing with them, of course, since they're low pass filter, they would suppress the noise. But again, they might make your system slower. Lead makes the system faster, no effect, not too much on the steady state. So what if you want to make everything better? Makes the system faster and bring down the effect of noise and bring down the steady state error. Well, if you want everything together, then you have to combine these compensators into a lag lead or lead lag, whatever you want to call it. So we're going to see how we can achieve these. So first, let's look at the lead compensator. What does a lead compensator do? So just like the same thing that we had in the Routh-Lucas method, the transfer function for a lead compensator is just like what we had in chapter 6. It has a gain, it has a zero, and it has a pole. The zero is at -1/3, and the pole is at -1 alpha times t. And the gain is called Kc. Alpha is a number that is less than 1. So what does it mean in terms of zero and pole? So let's say t is 10 and alpha is 0.2. So what does it mean? The zero is at 1/10 and the pole is at 1/0.2 times 10, which is 1/2. So what does that mean? It means the pole is closer to the origin than the zero, right? Because t is bigger than alpha t and you're dividing by t, so this whole number has a smaller magnitude than this one, right? So if you have a pole and a zero, the zero is further away from origin, the pole is closer to the origin, and that's exactly what we had in the previous chapter. So no difference. By the way, the name of alpha, we call it the attenuation factor. Another way to show this is we multiply both numerator and denominator by alpha times t. So we multiply both numerator and denominator by alpha times t. If we do that, then in the denominator you get 1 plus alpha ts, in the numerator you get 1, you get alpha plus alpha ts. If you factor out that alpha out of numerator and multiply it by kc and then call the result what? K, then you can also write it as k 1 plus ts divided by 1 plus alpha ts. And why should we write it this way? Let's see if you remember. Why, instead of what we did in the previous chapter, we write it like this? Yes, you're right. Because I told you, whenever we want to do Bode plots, we always make sure that the constant term in numerator and denominator is equal to what? To 1. So instead of this initial form, I use what? This second form. Okay, let me clean this up. So again, I really try to only use this format in this chapter. That's the same as previous one, but this is more comfortable for Bode plots. So that's the definition, and then this is the relation between kck and alpha is less than 1, which we call it attenuation factor. Good. So now let's look a little more in depth into this compensator, the lead compensator. If you look at the Nyquist plot of this compensator, if you plot the Nyquist plot for this, it looks like a semicircle. And the maximum phase contribution that it can create is phi m. If we show the maximum phase of this by phi m, this phi m is a factor of alpha. It is a function of alpha. How? Sine of the maximum angle contribution, the maximum phase contribution, is equal to 1 minus alpha divided by 1 plus alpha, and the proof of that is from this shape that you can see here. But I'm not after proving, so I don't go into showing why this is the case, but you can just look at this picture and refer to your textbook if you want to see that. We call phi m the maximum lead angle, the maximum contribution. Now, it might be a little hard to see it in this Nyquist plot, but if I show you the Bode plot, that's where you can see that phi m much better, and that's why we prefer Bode plot. So this is the Bode plot of a lead compensator. If you look at the phase plot, you see at low frequencies and high frequencies, it does not contribute anything to the phase of the total system. The phase of it is 0 and 0. But as you're going through to mid-range frequency, you see at some point it gives you maximum phase contribution, and that maximum phase contribution, phi m, again, it's a function of alpha that you just saw, but where is it happening? The place that this maximum frequency, the place that this maximum phase is happening, at what frequency it is happening? At this frequency. Omega m equal 1 over square root alpha times t. By the way, here this t is outside the square root. If you don't like it, you can write it like this. Okay, so this is the frequency at which the maximum phase is happening. Now in this plot, as you can see, this plot is drawn for alpha equal 0.1. So if you plug in 0.1, this will be simplified into square root 10 over t. But in general, this is the general formula for where that maximum phase is happening. By the way, I said this is a high-pass filter. How can you see? Well, just look at the magnitude plot, right? Look at the magnitude plot. So at low frequencies, what is the decibel? It's a very small decibel. And you know, negative decibels means what? It means magnitude is less than 1. But when the frequency is going higher, what happens? Your decibel is going back to 0. 0 means the magnitude of gj omega is what? 1, right? Because this is 20 log of magnitude. So whenever I have 0 decibel means what is the magnitude of g of j omega? Or g of c, let's call it g of c because that's a compensator. This is equal to 1. In other words, it does not attenuate the input when you want to convert it to output. If you send into this compensator a harmonic of magnitude 10 units, it gives you back output of 10 units. It's not going to bring the magnitude down if the input that you passed in has a high frequency. Okay? On the other hand, if you pass to it an input with a low frequency, what happens? It is something like negative 20 decibel. And negative 20 means the magnitude is what? Yes, it is 0.1. So it reduces the amplitude of input to 10% of it in the outputs. Okay, so basically suppressing low frequencies while not suppressing high frequencies. That's why we call this a high-pass filter. And that is kind of similar to a derivative, a little better than derivative, a little more gentle than derivative, but that's the effect. It will amplify high frequencies. Noises are high frequency signals. So it is not doing anything with them, but low frequencies, whenever you want to pass a low frequency, it's gonna basically kill that low frequency. Okay, so this is the behavior of this filter, and again, the important formulas for us is 1, the location at which the maximum phase contribution is happening, and then the maximum phase as a function of alpha. These two are extremely important. We use them a lot. Now, let's say if we want to design a lead compensator, how do we do it? So it has several steps that we have to go through from 1 to 6, and I explain them as I go over this example. Okay, so first, let me tell you step by step, and as I said, each step, I go and apply to the example, then I go to the next one. So I'm not going to read all from 1 to 6 and then come back here because you're going to forget it. So each step I say here, I go and apply to the problem right away. So when you want to design a lead compensator, what is it that you do? First, it says if the planned transfer function is G, you determine the gain K, this gain here, such that the new system G1 equal K times G satisfies the static error constant requirement or the steady state error. In other words, the first thing you do, so this is G, okay? This is G of S. The first thing you do, you add a compensator. As I said, you have to add a compensator right before G. You call it the lead or lag or whatever compensator. The first thing you do, instead of using GC of S to be what? K times 1 plus TS over 1 plus alpha TS, all you do for the first stage, you assume that, well, I do not have this polar zero. All I have is my compensator is a simple gain. Okay, so for the first step, you assume that it's just a gain K, no zero, no pole. Can that help me achieve at least the first requirement, this one, the static error? First of all, what is the current static error, and then how much are we going to increase it, and what does it mean about the steady state error? Let me refresh your mind. So what is the current KV? If somebody says, if I do not use the compensator, let's say I don't have this compensator, I only have G, what is the KV for the current system without compensator? Do you remember the formula for it? KV was the limit of S times GS as S goes to 0. Hopefully you still remember. So that's the limit of S times what? 4 divided by S times S plus 2 as S goes to 0. So these two would cancel out. You're going to get 2 units. So the KV of the system that is not compensated is 2 second inverse. But I wanted to bump it up to 20, so I want to make it 10 times bigger. And why should I do that? Because if you remember, if this input is U and the output is Y, what's the importance of KB? Yes, if the input U of T is a unit ramp function, T, what was the steady state error of the system? The steady state error is 1 over KV. So the bigger the KV, the smaller what? The steady state error. So if it's 2, means the steady state error is 0.5 units. Well, if it's 20, it's 0.05 units. So the bigger KV, the smaller the steady state error, and means the better controller, the better control system. So we always want KV to be as big as possible. Here, we say at least 10 times bigger. And so, as I said in the beginning, what I have is 2 units. So how can I force this to go up to 20 units? Well, as I said, I add a compensator, which is only a simple gain first. If I do that, what's the difference? Now, when I want to calculate KV, it's not simply limit of SGS, it's limit of combination of these two. S times combination of these two as S goes to 0. So it's not SGS, it's what? S times GC of S times GS. You have to bring this guy in because these two are in series. The equivalent transfer function is the product of the two. So what happens? Yes, a K will be added here. And so this is going to be what? 2 times K. And now this 2 times K, we want it to be equal to what? 20, what does it mean about K? Yes, if I use a gain of 10 units, then I can bump up this KV from 2 to 20. So this is not the only thing that we need to satisfy here. We also need the phase margin of at least 50 degrees and gain margin of at least 10 decibels. So now the question is, now that we only added the gain, what's the situation of the system in terms of phase and gain margin? So that's this stage number 2. It says consider this new only gain modified system G1, which is K times G with that K of 10, and draw the Bode diagram of that and evaluate the phase and gain margin. Okay, see what they are. So let's do that. So our system is 4 over S divided S times S plus 2 and then multiplied by 10. Okay, so this is what we do. We say system is a transfer function of numerator is 40 and denominator is S times S plus 2, which is S squared plus 2S plus 0 constant. Okay, so that's our system, and then we say give me the Bode plot of this system. And then we determine the phase and the gain margin from there. Now, you know that when I want to click on this Bode plot, most of the time I jump from one point to the other because the number of frequencies used in drawing this plot is not typically a huge number. So maybe before you do that, you want to define a kind of frequency range with a lot of points, data points in it, so that you can move smoothly on this curve and you can get phase and gain margin quite accurately. So what I recommend is first you define a range of frequency, omega equal log space of, and then from 10 to the negative 2 to 10 to the positive 2 maybe, and maybe 1,000 points or something like that, a lot of points. And first say Bode of system and this omega, which is the same but with a lot more points, and then also turn the grid on if you want. You don't have to, but now let's find the gain and phase margin here. So if you want to do that, we use the data tip. For the phase margin, we have to find the gain crossover frequency, and that's where the magnitude becomes 0, which is roughly here. So if I click, you see that's 0.281. I move to the right, and you see this is 1.12. This is 0.02. That is the closest you probably can get to 0. And you see the gain crossover is 618 radians per second. And now we calculate the phase of the system at the very same frequency here. So we try to click at the same point. There are corresponding points. So we go to 618, which is here. And you see the phase right now is negative 162. So how much is phase margin? Yes, phase margin is 180 plus this number. So if I want to insert it as a text box, here I can say that phase margin is equal to 18 degrees, right? That's the phase margin, which is negative 162 plus 180. And then if I want gain margin, then I add one more data tip. And let's do that. So here we need the frequency at which the phase becomes negative 180. And clearly you see it does not get to negative 180 at any point until this frequency keeps going. Even if you draw this, here is 100 radians per second, but even if you draw this to 1,000 or 10,000, this phase will ultimately converge to negative 180 when omega is going to infinity. Nowhere else you have omega of negative 180. In other words, the phase crossover frequency for this system, let me draw it again here. So the phase crossover frequency is infinite. There is no finite number for phase crossover. You remember that the gain crossover frequency, where the gain passed from 0.0, so gain crossover frequency in this system was 618, almost. And what is gain margin? When omega goes to infinity, what is the magnitude of the system at infinity? Well, it's infinite, of course, because this guy is going to infinity, negative infinity as well. And then opposite of that, the magnitude with the negative sign is the gain margin. And so what is gain margin in this system? Yes, the gain margin is infinite. Okay, so this is the Bode plot for G1. Okay, so if I can insert a title or modify the title, this is for G1 of S, which is the same as K times G of S. Okay, and of course it is going to write it on the top of the previous one, which you can go and modify and delete it, but because that's the default of Bode plot. So now, is that enough for us? If we go back, we see that no. Well, of course, gain margin is good. It's infinite, way more than 10 decibels, but the phase margin is 18, should be 50. So we have some amount of angle or phase that we need to contribute. And how much? Well, since it's 50 and we have only 18, so we would say we need 32 degrees of phase that we need to contribute, right? So based on that, here is what we go to step number 3, the amount of phase lead angle that we need to contribute. It says not only use that number that you calculated, which is the difference between 50 and 18, 32, also add some additional 5 to 12 degrees to it, because when you add a lead compensator, it moves the the gain crossover frequency, and the final thing will be less than what you assume. In other words, if I only set alpha from this formula to contribute only 38 degrees, exactly as much as I need, okay? And then I design my compensator based on 38 degrees phi m, and go back and look at the new system with phi m of 38 degrees, I'm going to see that if I redo the Bode plot for that, the phase margin is not going to be 50. Although I designed it for 50, but because the gain crossover frequency changes its location as a result of adding compensator, you're going to see that the phase margin of the system will go down to probably 45 degrees instead of 50. So it says add some 5 to 12 degrees on the top of what you need from your calculations to make sure that you get that 50 degrees that you want. Okay, so here I would add 5 degrees, right? So if we go ahead and look, how much was it that we needed? So let's go back to that graph. It's 18, I need 32 degrees. So I need to add 5 to 12 degrees to this. So anywhere from 37 to 44. Anywhere in that range is the required phi m. Your textbook used 6 degrees because your textbook calculated the phase margin to be 17 degrees instead of 18. That's what your textbook says. Well, we can go with that too if we want. We can say, well, because this is not exactly 162, this is 162 point something, okay? So when you round it up, the textbook says this is about 17 degrees, right? And so this number that it calculated So it's considered it 163, that is 17. So we need 33 degrees. And then it added 5 more degrees, so made it 38. So that's where the textbook here, let me write it on the top of this slide for you. The textbook says I need phi of m equal to what? 50, which is desired, minus 17, which is what I have, plus some additional 5 degrees to be safe. So it is 38 degrees. Okay, so this is what you want to achieve. And then now it says, okay, sine of this phi m, which is 38 degrees, is equal to 1 minus alpha divided by what? 1 plus alpha, right? This formula that you can see here. And then from there, you can calculate, of course, what? Alpha, the attenuation factor, which is extremely important. And if you see your textbook, the number for alpha turned out to be 0.24. Okay, so I write it here for you. So sine of 38 degrees is equal to 1 minus alpha divided by 1 plus alpha. From here, if you solve for it, you can see alpha should be 0.24. That's the attenuation factor, which is clearly less than 1, and everything looks good. So now we have gone through this stage number 3, and we determined alpha. Okay, what else? Now that we have that, it is time to determine Kc, of course. That's not really much needed, but if we want, we can say Kc is K divided by alpha. So if we want, we can do that. All right. But again, it's not really much needed, but you can divide that and get the number, which in this case, this is going to be more than 40, right? 4167. So the only, again, this step is not really much needed. Okay, so if you want, you can add something here and say, well, this step is not mandatory. Because you can either show your compensator by the first formula or by the second formula, right? No difference which one you use, this one or this one. The only parameter missing is t, and let's find t. So it says, where do you find t? It says, we want the location of omega m, where the maximum lead angle contribution is happening. We want that location to be what? The new gain crossover frequency. In other words, what we need is, we want omega m equal 1 over t times the square root alpha to be the new gain crossover frequency. Well, how can that be? If I go back and look at my Bode plot, look at the gain crossover frequency that I have, right? At the gain crossover frequency, which is at 618, correct? This is the system where the magnitude of K was equal to 10, but no zero or pole added. It was just gain modified. Now the question is, I don't want this 618 to be the new gain crossover frequency. I want this value. I want this value to be my new gain crossover frequency. So I want at this frequency that's the magnitude of GC times G, the whole new open loop transfer function. I want this, to be 0 decibel. And this number is different, of course, than 618. How can I do that? Well, the way to achieve it is whatever at this point the magnitude of the compensator is, at this point, whatever the magnitude of the compensator is, that value, which as you can see is a negative value, if I add that to the positive value of the original G, and make sure, let's say if this is, for example, in this case, is negative 10 decibel, right? That comes from the compensator. And then the magnitude of the G, the original system itself, is positive 10 decibel. If I add those together, then at that frequency, I have a magnitude of what? 0, right? Negative 10 plus positive 10. So the question is, at this frequency omega m, how much is the magnitude of the compensator? And you can easily show that at this frequency, the magnitude of the compensator alone, just the compensator alone, is equal to 20 log of 1 over square root alpha. This is the magnitude of the compensator for arbitrary alpha. So now I look into the Bode plot of G1 of j omega and look for a point which magnitude of it is negative 20 log of 1 over square root alpha. When I add these two numbers together, I get what? I get 0. So wherever the magnitude of G1 is equal to this number, that is going to be my new gain crossover frequency, and that is equal to 1 over t square root alpha. From there I can find t. So look, I go and first I calculate 20 log of 1 over square root alpha, and how much is that for this alpha of 0.24? So 20 log of 1 over square root alpha to the base of 10 for that alpha, if we calculate it, it is 6.2 decibel. So now I look into this plot for G1 and I find a place at which the magnitude is negative 6.2 decibel. So I use my data tip again, and I look for a place with negative 6.2 decibel almost. And you see this is negative 7. I try to go close to negative 6.2, and you see that's almost 8.93 radians per second, not the previous one, 618. So I want my new gain crossover to happen at 8.93. Your textbook rounded it to 9. So your textbook says, well, I want the new omega m to be 9 radians per second, and this guy is equal to 1 over t square root alpha. I know alpha. From here I can find my t, and t will turn out to be 1 over 4.41, which is 0.23, I can call it, if I want 2 decimals. Okay, so now I have my t, now I have my alpha, and I also found my kc, and therefore I can completely form my compensator, right? So now if I do it, my compensator GC of S is going to be KC, which was 4167 times S plus 4.41 divided by S plus 18.4. Okay, that's my compensator. And G was 4 divided by S times S plus 2. Now my new open loop transfer function is GC times G. So I multiply these guys together, and now I draw the Bode plot for this new one. Okay, so I multiply and draw the Bode plot for this new one. And let's see if this new system satisfies everything. For sure, it satisfies the KV because we said it that way. Now, what about the phase and gain margin? So now I define my system to be differently. So now that KC 4167, right, is multiplied by a 4 and multiplied by the 0 of the result. Okay, so this is the numerator. The denominator is that guy convolved with S plus 18.4. Use S1. Okay, so this is now the new compensated system, and now if I say Bode of this system and omega, and now I try to find the phase and gain margin of this system. So first, where is it that the gain becomes 0? I find the new gain crossover frequency, which is somewhere here. You can see it's almost 9 radians per second, which is what we wanted. Now at that frequency, I want to look at the phase of the system. It should be more than 50 degrees or so, or about 50 degrees. And you see it is, right? Look at the phase of the system. It's 130, and when you add 180 to it, what would you get? 50 degrees. So you see, although I added 5 degrees extra, but now that I calculate my new phase margin, it is exactly 50 degrees that I wanted. It's not 55 because the gain crossover frequency shifted. And now, where is the frequency at which the gain becomes negative 180? Again, you see, it doesn't happen until omega goes to infinity. And so at infinity, of course, the magnitude of system is negative infinity. So the gain margin is what? Still infinite. So the gain margin is infinite, which is way more than 10 decibel that you need, but the phase margin is exactly 50 degrees that you wanted. So your compensator is designed and you got what you want. Okay, thank you so much. I'll see you in the next lecture.